All right, 311. Okay, so kind of a new topic, but still continuing with MOSFETs. We're going to cover today the H bridge, and you're going to see exactly why it's called an H bridge in about a minute here. So first, let's go ahead and ask a question. That question is, say I got a motor, and I want to can make it turn clockwise as well as counterclockwise. Well, how do I achieve that? How can I do that? Well, if we go ahead and take a standard motor, and I'll use my motor schematic symbol over here. Let's give ourselves a motor. I'm going to put this in red. All right, and let's do this. Circle with an M gives us a motor. And I'm going to take one side, attach it to, let's just stick with 5 volts for now. Take the other side and attach it to ground. Well, which way is my current direction going to go through this motor? Well, it's going to go to the right? It's going to go from higher voltage to lower voltage. And let's just say that if the current direction goes in this to the right, that my motor is going to turn clockwise. Now, given this same exact motor, what do I do if I want to turn this motor in the other direction? Instead of going clockwise, let's say I want to go counterclockwise. Well, what I do is I just change the direction of the current, make the current go from the right to the left. If I do that, I'm going to get a motor that actually turns counterclockwise. So let's go ahead and put that up here, for example. I'll take my motor. Now I'm going to take the right side, attach that up to 5 volts, and take the other side and attach that to ground. And now my current's going from right to left. And if I do this by the convention that I've already established on my sheet here, my motor is going to turn counterclockwise, or anti-clockwise if you're in Europe. All right. And that's great. So I disconnect my motor, I flip the wires, and now my motor goes in the other direction. Cool. How do I make a computer do that? Well, my computer doesn't exactly have little robotic arms that can disconnect the wires and reconnect them in the other orientation. So I need to come up with another way to achieve the same effect. And that is the goal, that is the purpose, that's the motivation for the H bridge. So I'm going to go ahead and draw an H bridge using our abbreviated MOSFET schematic symbols. So let's do that. I'm going to give a common VCC, and I'm going to go ahead and I'm going to place some P-channel MOSFETs on the top. And I'm going to place some N-channel MOSFETs on the bottom. And now my motor that I want to get the current to go in both directions through, I'm going to place that in the center. Okay, and now let me go ahead and point out a couple of things here. Notice that on the bottom here I have two N-channel MOSFETs because I need N-channel MOSFETs to achieve low side switching, right? If you think about half of this circuit, well, half of this circuit I have what's referred to as a half H bridge. Notice here I have a P channel as my pull up, and I have an N channel as my pull down. So my P channel is being responsible for pulling this side of the motor to VCC, and similarly I have a low side switching circuit here, my N channel MOSFET, that's responsible for taking this same wire and being able to pull it down to ground. And then on the other side, I have another half H bridge. Again, the same thing. P channel is responsible for the high side switching circuit, pulling this side of the motor up to VCC. And I have an N channel MOSFET whose job is to be able to pull down this side of the motor to ground. So make sure you take a look at the last lecture where I talked about the high side switching and the low side switching. There's a reason I have to use a P channel up here and I have to use an N channels down here. Okay, so let's roll with this. Now, the H bridge, as I mentioned before, why do we get this name H bridge? Well, first off, this looks like an H, right? Second off, it's a bridge circuit. I have two parallel elements connected into the center by some load, in this case, the motor. So this is a bridge circuit, and it looks like an H, so H bridge. Now, let's go ahead and say that I have taken this side, and each one of these MOSFETs is essentially acting like a switch. So let's go ahead and say that this one is closed. This one is behaving as though it's closed. And these two are behaving as though they're open. Well, notice what this ends up turning into. VCC, closed switch, open switch, open, closed, with my motor attached to the center. Now just look at these switches, these MOSFETs. Notice my P channel on the upper left is now closed, providing me a pathway that connects this side of the motor to our positive voltage. And I have a corresponding N channel down here that is acting as though it's closed, pulling this side of the motor down to ground, giving me minus over here. Notice which way my current's going to go. My current is going to go from VCC through this MOSFET, through my motor in this direction, and it's going to go to ground through this MOSFET down here, this bottom N channel. And when that occurs, remember, my motor is going to turn clockwise. Now, similarly, if I change my inputs to these MOSFETs here, all four of them, then I can go ahead and create a different situation. I could make this one closed, this top right P channel, and I could make this bottom left N channel closed, and then I can open these remaining ones. Now watch what the corresponding circuit looks like if I achieve that. if instead of this, I alternate which MOSFETs are closed and open, notice which way my current direction is now. Now, this upper P channel MOSFET is pulling this side of the motor up to positive, and this corresponding N channel MOSFET is pulling this side of the motor down to ground. Notice my current direction. Now it goes through this MOSFET, through my motor in this direction, and down to ground. Well, notice if I do that, now my motor is going to turn counterclockwise. So this H-bridge allows me to create a situation where I can take any load, regardless if it's a motor or just some resistor or an LED or anything, and I can cause current to go in one direction as well as change it and cause it to go in the other direction. Okay, now all we have to do is make sure that we drive these MOSFETs correctly. And if we do that, we can get this to work. So let's go ahead and build on the circuit and just add some control circuitry in order to get that desired effect. Okay, let's go ahead and create this H-bridge out of real proper N-channel, P-channel MOSFET schematic symbols and create the control circuitry in order to achieve that desired effect. I'm going to take 5 volts up here. I'll just work with 5 volts for this example. Now I'll add my N-channel MOSFETs. And I'll create my ground over here. Let's add our motor to create that bridge. And now remember the pattern that we had to get. I need this one closed and this one closed, and these two to be open. And now let's look at how we would achieve that using these MOSFETs. Now, in order for an N channel to be closed, on the gate, I need to apply 0 for it to be open, and I need to apply a logic level 1 or 5 volts to make it closed. For a P channel, it's just the opposite. A 0 makes this closed, and a 1 makes this open. Okay, so it's just inverted logic at that point. I guess you can think of your P-channel MOSFET as being active low. It's when you assert it, you're actually applying a logic level 0 or 0 volts or a low voltage or ground. Okay, so I need a 0 here to make it closed. I need a 1 over here to make this one closed, this N channel. Up here, for this to be open, I need to make this a 1. And I need to make this one over here be 0. So it looks like if I want to achieve this kind of diagonal relationship here where the diagonals are closed and the other diagonals are open, I need to apply a low voltage to one side and a high voltage to the other side. So I can do this using an inverter. But before I do that, let's look at the other case. When I want my current to go in the other direction, I need this one to be closed. And I make this closed by applying a 0 over here. I need this one to be closed. And I achieve that by writing a 1 to it. Up here to the upper left, that P channel needs to be open. I achieve that by writing a 1. And down here, I need this N channel down here to be open, so I need to write a 0 to it. So we get this relationship. 0 on one side and 1 on the other side creates clockwise motion from my motor, or my current to go to the right. I'll keep the colors the same, so 0's on the left and 1's on the right. Creates my current going to the right. And if I flip that and apply 1's on the left and 0's on the right, I get my current going to the left. Okay? So again, I can do this with an inverter. So all we have to do here is take one signal here. Actually, I'll try to fit this all on one screen. And I'll bring some white out to the rescue. And then I'll take this input signal, put it into a digital inverter, bring that out to the other side. And now, when I write or I apply 0 volts over here, all of these MOSFETs on the left get 0. And I get 5 volts on the output from this inverter. So I get 5 volts, or logic level 1, applied to the right side. And if I go ahead and flip this, if I make this 5 volts, I get 0 volts on the other side of this inverter. So now I get a logic level 1 on the left MOSFETs. And on the right, I get 0. And that goes ahead and gives us our desired relationship where we get our current going to the left when we apply 0 volts, and the current going to the right when we apply 5 volts. But as I mentioned in the previous lecture, remember we have to use P channels for the high side switching, and we have to use N channels for the low side switching. And this is a proper H bridge. Okay, so incredibly useful circuit. I will say many of my designs in the workplace have utilized H bridges in some form or another. There are times when just a half H bridge, just one side, having a pull up and a pull down network, is incredibly useful. You'll see that a lot on switching power supplies and lots of other circuits, which is a bit out of the scope of this class, but this topology where we have a corresponding pull up for a pull down is incredibly valuable. And we actually saw that before. That's how you make an inverter. If you go back to lectures, I showed the internals of this very simple inverter. This inverter is actually a half H bridge inside of here. So if you really want to get picky about it, technically right here we have 3 half H bridges, 2 that create the H bridge under investigation here, as well as 1 half H bridge inside of here. So incredibly valuable circuit. It pops up all the time, whether you even know it or not. Okay, so I'm gonna leave this circuit as is, and next time we're gonna pick up on analog digital converters. I'm going to go over that before we get into op amps. Op amps are incredibly interesting, very useful circuits, and we're going to get there before the semester's up, but we're going to first look at analog digital converters, because a lot of what I have to say as far as the application for operational amplifiers before we get into it, I think is a lot easier to see when we have some understanding of an analog digital converter. Like I said, this class really is geared towards embedded systems and electronics that are valuable and useful, more useful for us as computer engineers and embedded systems, and interfacing with digital devices. So we'll take a look at the analog digital converter next time. All right, thank you.